Good morning. Here are yet again for another lovely session of CENG 4412 Steel and Concrete Design. This is going to be part 1 of the 16th lecture in the video series, and today we're going to be learning about Euler column buckling. So we have finished looking at both steel and concrete beams, including the deflection for each, and now we're going to start looking at columns, both steel and concrete columns. But today I have a few learning objectives. First of all, I want to derive the Euler column buckling equation. Second, I wish to compare actual columns to ideal Euler columns. Third, I want to define the effective length factor K. And finally, I want to plot the LRFD column length curve. So Euler column buckling. And I want to try to derive this equation. Euler column buckling. All right, so first let me define a few things. First, I'm going to look at a pin-pin column. Well, I'm going to be considering a pin-pin column and showing the deflection as a function of x is what I really want to get at. So consider a pin-pin column. And although I'm going to draw this as a really interesting pin, which is sort of a pin on a roller. And this is just so that to make it absolutely clear, basically what I want is I want this support, the vertical support, to be able to ride up and down as the column changes in height. So you wouldn't really build something like this, but it does. I just draw it that way to illustrate the theory. Because a real column will be able to decrease in height as it compresses, but for our illustration purposes here, I'm going to draw it kind of like this, as a column that is on a pin here and a pin up there, although it's kind of drawn like a roller, but really this is, what I'm trying to show is this is a pin that is free to move up and down. So, but ignoring that for now, just consider this a pin-pin connection. So pin and pin, and this is going to have a length L. Our column will have an initial length L. And I'm going to apply a vertical load P downward at the top. And of course, the same P will be produced as a reaction force at the bottom. P and P. And let's say this here is going to be this would be the initial configuration before the column reacts at all to the load. So this would be the initial configuration. And we, of course, know that after it buckles, it's going to bend more like this. So you've probably learned about buckling in mechanics and materials. But so you know that when something buckles, this is not necessarily a material failure. It's not that you're taking the column all the way up to the yield stress, for example. Rather, what is happening is you are taking it to a point where the geometry itself becomes unstable and it buckles to the side, either in a C curve for single curve buckling or maybe an S curve, et cetera, et cetera. And we'll talk more about that. But then I'll just concern myself with the first buckling mode, which is where it's just buckling out like this. And so I'll look at then the buckled, I'll draw next the buckled configuration over here. Buckled configuration. And so then let me label some things on here. I'm going to have the same rolling pin. And again, this is just, the rolling pin is just to enable the pin to slide vertically. And then I have the same fixed pin, well, vertically fixed pin here. But don't worry too much about that. This is just a pin. This for now is just a pin-pin connection. And so, although I think maybe I want to draw this, I want to put a little green line showing the initial vertical line here. Something like this. And this connecting to a bottom pin. Connecting to the bottom pin. And then the buckled shape is going to look something like this. If I can manage to draw an arc properly. Something kind of like this. Beautiful arc. Looks like a potato. Okay, so here then, I'm going to have coordinates x and y. I'm going to call x the x is going to be my axis along the length of the member. And y is going to be the perpendicular axis. So x and y like this, so I'm using local coordinates here. And then at any given height or any given location x along the beam, I'm going to have some y as a function of x. This is going to be y as a function of x. So by putting in a given x value, I want to be able to get a deflection equation. I want to be able to get not a deflection equation, but I want a deflection equation where I can put in any given x value and be returned the deflection for a particular x coordinate. Okay, so I need to make a few assumptions like everything else in engineering. So I'm going to make a few assumptions. And these are going to be a lot of our very common assumptions we use in this kind of structural and mechanical engineering analysis. So some common assumptions. Well, these shouldn't be really surprising to anyone. The assumptions, first of all, perfectly elastic, no big surprise there. Perfectly elastic. So we're ignoring any kind of strain hardening. Initially straight. So we're ignoring any kind of initial bending present. And really, I like this kind of example because I like this kind of derivation because it really connects the very intricate nature between bending and columns. There's a reason we cover bending before we cover columns, because especially with concrete, you basically can't have a pure axial force column. So there is going to be an intricate connection, a very intimate connection between bending and axial force, and we'll see that as we go on. Plane sections, so we're saying plane sections remain plane, and we talked about that in the previous lecture a bit, and in ones before that. So plane sections remain plane. Homogeneous and isotropic. Homogeneous and isotropic, so nice friendly materials. What else? Small deltas, so we're assuming small deformations, small deltas. Small changes in length, small deltas, and also concentric loading. So we're ignoring any kind of eccentricity in loading. If you ever have, what I mean by that, of course, is if you're not familiar with that term, if you don't remember that from mechanics, materials, structural analysis, etc. If you have, say, like a W section, imagine I use a W section as a column. And then imagine I apply, now it's concentric loading, is if you're going to apply basically loaded right about the centroid here. So if I apply a point load into the page here, this would be concentric loading. But then if I did it somewhere else, maybe the centroid of the load was off center a bit, like I could draw it maybe, I don't know, in blue here or purple. If I put load somewhere over here, or somewhere over here, this would be eccentric loading. And the problem with that, which there are ways to design for, and it's really not too bad, but you got to deal with something called the P delta effect, which I think we'll not quite get to in this course. It's a bit beyond the scope of the course, because if you have the problem with eccentric loading is if the load is not lined up exactly with the centroid of the member. In other words, if I apply the load P here, maybe I'll exaggerate it and say the P is maybe over here, something like this. Well, that P then, we're going to have, because it's off center, you now have a moment arm, you have a separation, you have a moment arm, you have a moment. So this would be like a small L here. And so based upon that, you're effectively putting a moment equal to PL on the end of the member. But we won't worry too much about that. So you'd be applying a moment, by having an eccentric loading, you'd be applying a moment of PL to the end of the member. But don't worry too much about that for now. Okay, just wanted to describe what the assumption of concentric loading is and what its significance is if that's not true. Okay, so what I want to do next is I want to cut the column at X. I want to do sort of a method of sections, very similar to what we do in statics. or mechanics of materials or many other structural analysis type courses. I want to cut the column at X and make a free body diagram. And make a free body diagram. And draw a free body diagram. And I'm going to do this from the bottom end here. Okay. So I'm going to look at a section of this column. And let's consider this here. And I'll have some section of the column that I've cut out. It's like this. And I'm going to have two forces here. Well, a couple forces. Let's just show all the forces. On the bottom end, I just have P. Then reacting to that, I have some P internal. Then I have some M internal also present here. Some internal moment also present. And then I'm going to have some deflection Y there. So that's my initial configuration, and I have some sort of Y here at X. Some Y at X as we described previously. Here, let's see. First of all, if I do a summation of forces in the vertical direction, well, that's fairly straightforward. Summation of forces, I guess I guess I can say in the X direction to be consistent with what I've done previously. Sum of forces in the X direction equals 0. So therefore, P internal at that point must be equal to the end load P. Not really any surprise there. Then if I do sum of moments at the bottom here, if I do a sum of moments at the bottom, basically this means that I'm going to have 0 moment overall. So the sum of moments at the bottom must be equal to 0, or I can say that this would be P internal times Y at X minus M internal must equal 0. And all this is a basic statics equilibrium. P times its moment arm. And this P here, of course, if I'm summing, this is the point I'm summing moments about here, it's not going to generate any moment about that point, but the P internal will and the M internal will. And I'm going to refer to this as equation 1, which I'll reference as I go along. Then I need a few other things. I need to borrow some things from mechanics and materials, some deflection equations from mechanics and materials. So I'm sort of just building up the pieces of the Euler column equation. So from mechanics of materials, so first of all, I want my phi, my curvature. Phi is going to be equal to 1 over rho. Phi is equal to 1 over rho, which is also equal to m over EI. Equal to m over EI. And I also know that 1 over rho, these are just equations from, again, mechanics of materials. 1 over rho is equal to negative y double prime of x. Negative y double prime of x. And I can combine all these together and say, okay, well, m is equal to negative EI y double prime of x. And these are just things from the deflection derivations in mechanics of materials. And this is maybe equation 2 here. Okay. So questions so far. I'm just gathering a few things up from statics and mechanics of materials. Next, I want to substitute 2 into 1. And I will get that EI times y double prime of x plus p times y of x. P times y of x is equal to 0. is equal to 0. So I have a nice, lovely differential equation here. And I'm going to rewrite this now here, and I'm going to introduce a quantity k, just to make things a little bit easier. K, where k is not really a constant, but is going to be equal to p. It's going to be equal to p divided by root ei here. Root ei. So if I then work through this, basically I can say that this is then equal to this here is going to be equal to y double prime of x plus k squared times y of x is equal to 0 here. There. And so basically this is now a second order differential equation. Equation with constant coefficients, at least constant in the context of x and y, with constant coefficients. And that means I can now apply the Euler solution. If you remember your dvq, not an Euler particular solution, but just a solution to this type of equation. So the general solution for this form of equation is, so again, Euler solution here. But for that type of differential equation, the general form of that is going to be y of x is equal to a times the sine of kx plus b cosine of kx. Plus b times the cosine of kx. And again, this is the general solution to this type of equation. The general solution. And that's the general solution, not to be confused with the major solution or the kernel solution or the lieutenant solution. Wait, that's something very different. That's not a Halloween joke. It's a really bad military joke. I started the class by saying, guess what we're going to learn today? It is Halloween, so I did start the class today by saying, guess what we're going to learn today? Euler column boogling. Oh boy. Okay, so let us apply boundary conditions. So if we apply boundary conditions to solve this equation, well, I know, first of all, that y of 0 is 0. And so by looking at that, if y of 0 is 0, I in then turn know that 0 plus b is equal to 0. Because again, if I put in 0 for x and y, I'll just get that b is equal to 0. And then if I put, I also know that y at L is also equal to 0. So if I substitute in L here, I basically get, let's see, I will get essentially that 0 is equal to a sine times KL, or a times the sine of KL here. A times the sine of KL, because I can do this. The sine term is the only one present because the b is going to be equal to 0 again. Because of the first condition. So there we have that. And then, from this, we have two possible solutions. If we know that the a sine of KL is equal to 0, we have two options. We have two ways to solve this equation. First, we could say that a equals 0, but that's the trivial solution. We're not really concerned with that because that just makes the whole equation equal to 0. We don't really learn anything from that, so we're going to reject that one. And the alternate one is where we get a condition where the sine of KL is equal to 0. So this equation will be true where the sine of KL equals 0. So, and that's the one we're going to work with. And so sine of KL is going to equal to 0 at certain periods of the sine function. So sine KL equals 0 when KL equals 0, or is equal to 0, pi, 2 pi, basically repeating endlessly over to n pi. this is just a trigonometry thing. It's going to be 0 whenever you have a certain pi term. So in turn, our overall KL is equal to n pi. KL is equal to n pi. And putting back in the k that we had previously, root p over EI, times L is equal to n pi. Or, solving all this nonsense for p, we get that p is equal to n squared pi squared EI over L squared. And this is the full form Euler buckling equation. This is the full form Euler buckling equation. And so you can get, now the interesting thing here is that you have, yes, question?
Are those two L's the same coefficient?
Are these two L's the same?
Is that L the same as the one above it?
Yes, the two L's are the same, yes. Okay. This is the Euler buckling equation. Now, the critical case is I want to talk a bit about this n factor. This is the Euler buckling equation. And you may remember this from mechanics and materials. This is the Euler buckling equation. However, and we have the critical case here. The critical case is where n equals 1. Critical case is where n equals 1. But what do I mean by those different n values? Let's remind us here. So basically we have different buckling modes, is how I would describe this. So when you put in different constants for n1, 2, 3, these correspond to different geometries of the buckling column. So the critical case, and again, the higher the n, the higher the buckling mode, the higher the buckling load. And so the critical one is going to be your n equals 1. But anyway, just to describe what these mean, and imagine, let me just draw out a series of columns and show what the buckling mode for each n would be equal to, or the geometry for each buckling mode would be like. So if you had n equals 1, let's do n equals 1, n equals 2, and n equals 3. So if you had, so maybe I can just call this buckling modes, or Euler buckling modes. Euler or Euler, depending on your preference. Euler buckling modes. And so here, if you had n equals 1, this is our bog standard buckling like this. If you have n equals 2, you're getting buckling something typically more like this, kind of like an S-curve. And n equals 3, this is essentially the number of buckling zones that you're having. N equals 3 would be something like this. And you can get these higher modes if you brace somewhere in the middle, but we don't need to worry about that right now. Okay, again, that is just going to be the Euler buckling equation. This is kind of the idealized form. So I'd like to sort of draw a comparison between Euler buckling and sort of plastic behavior, or a plastic bending moment that we had when we looked at beam bending. So here, Euler buckling is so basically Euler buckling is sort of an idealized case. It's looking at purely idealized elastic behavior. You're not dealing with any kind of local failure. You're not dealing with any kind of global failure. I guess Euler buckling is a global failure, but you're not dealing with any kind of properties of the section itself, really, beyond just moment of inertia. And so Euler buckling, basically, let me give you an analogy. Euler buckling is to columns. Remember those analogies from the SATs? Do they still have those on the SATs? I think they got rid of those, I guess. But basically, if I want to use an SAT analogy, Euler buckling is to columns as plastic moment capacity. Fully plastic moment capacity is to beams. Moment capacity is to beams. is to beams. So in other words, both of these are idealized states, are idealized upper limits based purely on elastic beam/column theory, or just elastic theory. Based purely on elastic theory. In reality, they occur only at very short lengths, at relatively short lengths. Past a certain length, other failure modes control. Well, actually, in reality, I should say there are other things there are other possible failure modes we will need to consider. There are other possible failure modes we will need to consider. We will need to consider. Here, and we'll talk about that in a bit. So I think actually I might stop this video here and I'll have a second one that we'll record immediately for looking at this more in terms of a more realistic or code approach. All right, thank you.